I'm going on. So here's my talk.
Okay. So
I'll come down and listen to you as long as you make sense out of Rayleigh-Taylor mixing.
I hope you are hearing my voice. Okay. It's not easy for me to give a talk after Professor Germano's talk, and of course after this nice discussion. So I don't really want to interrupt, but sorry for that. And thank you for having your time, by the way. It's coffee time. I know. I'll keep it short.
If you let us ask you questions while you're talking so that we can understand.
So my name is Yilmaz. I'm from Istanbul Bilgi University. I'm coming from Istanbul, Turkey. As you understand from the long title, I'm on the numerical side of turbulent mixing phenomenon. So what I do is to develop numerical methods with some nice features to analyze the flows with, let's say, challenging physics. Recently, I proposed an LES algorithm. Yes, it's an LES algorithm, which, as I said, it has some nice features as listed here. It's non-dissipative, fully implicit, discrete, kinetic energy conserving at discrete level, and it doesn't need to use Bose-Oberbeck assumption. It doesn't rely on this assumption. So maybe, theoretically it makes it more accurate physically compared to the other numerical methods. And of course, these features make it suitable for some kind of flows. So, for example, low-Mach number flows, or variable density and viscosity flows, and thermally and buoyancy affected flows. Driven flows. Rayleigh-Taylor instability. These type of flows are mainly hydrodynamic instabilities. So the Rayleigh-Taylor instability is one of them I studied. I actually solved Rayleigh-Taylor instability using this method at low to moderate Atwood numbers. Now I am trying to show that in the study, the method I propose can handle the high Atwood numbers Rayleigh-Taylor instability problem.
So what is the Bose-Oberbeck assumption?
So you simply, yes. You simply limit the changes in the density into the buoyancy term.
It's a buoyancy thing.
Yeah,
It's not a Reynolds stress thing.
Yeah.
It's called a Bose-Ness approximation for the Reynolds stress to make it an anti-viscosity.
Yeah, it's yeah. There's something. Yeah, there's some confusing there. I'll come to that point. Okay. So another aim of this work is to analyze the. I want to show the physics of high Atwood number can be captured or reproduced by this algorithm, by this LES algorithm, and as a secondary aim, I want to observe the effects of higher Atwood numbers or large density ratios on the Rayleigh-Taylor instability. So, here is the equations solved by the algorithm. They're fully compressible Navier-Stokes equations in conservative form with buoyancy term. And I made them non-dimensional. Look at the pressure. The way of making pressure non-dimensional is a special trick that allows you to study low-Mach number flows. It's called incompressible scaling. And of course, this is an LES algorithm. I need to apply far filtering. This is the result of far filtering. As you mentioned about, this is the eddy viscosity assumption or Bose-Ness assumption, which is different than the Bose-Ness approximation I mentioned before. So I had to employ a subgroup scale model.
So why do you use that?
Yeah, I'm coming. I'm coming. So the subgroup scale model I employed here is the Rayleigh model. It's one of the most efficient, well-known models. To my knowledge, to the best of my knowledge, this is the first time the Rayleigh model is applied to high Atwood number Rayleigh-Taylor instability, high Atwood number multimode Rayleigh-Taylor instability, to the best of my knowledge. Please correct me if I'm wrong. This is some other details of discretization. I'm skipping the details because of time limits. I also developed an LES solver. I gave it a name. I gave a name ILES, which is different than ILS or miles, please, because the implicit nature is coming from its discretization. It's not coming from its dissipation. So implicit LES is not an implicit LES, or it's not an monotone integrated LES. This is an in-house solver, as you understand. I made it fully parallel with PETC. It shares the same features with the numerical method. Additionally, I solved the linear systems arising from the discretization using incomplete LE preconditioned GMRS, which is an efficient approach. Make it faster, everything.
Could you comment one more time? What's the difference between your implicit LES?
Yeah, the term here represents its fully implicit nature coming from the discretization. Okay, so the term used here, implicit LES or monotone integrated LES, it comes from the dissipation. Okay, so let's focus on the problem. This is the, as I mentioned, very Rayleigh-Taylor mixing problem. It happens, you know, when a heavy fluid on top is supported by the light fluid at bottom against the gravitational collapse. But initially, the system is in hydrostatic equilibrium. Okay.
It's the upside down bottle problem.
I'm sorry?
It's the upside down bottle problem.
Okay, thank you. But when it's subject to perturbations, then the equilibrium is lost, and with the help of baroclinic vorticity contribution, flow evolves into a fully non-linear region as a kind of is a state of turbulence. At late times, bubbles and spikes are formed. Bubbles of light fluid rise up through the heavy fluid, and spikes of heavy fluid falling down through the light fluid into the light fluid, right? So this motion is controlled by the Atwood number. Here is the Atwood, the famous Atwood number.
When your friends,
I'm sorry.
they know you work in turbulence, and you say the word turbulence, and
Yeah.
then they say, "Well, what's that?" What do you tell them?
Again, please.
You said it was kind of like turbulence.
Yeah, it's
So
a state of turbulence.
What do you mean by turbulence?
It really doesn't satisfy the Kolmogorov's 5/3 rule. It's very close, but not really satisfy. That's what I'm saying. It's a state of turbulence. Okay.
You said you do variable density. Why do you assume constant density in the pressure? I don't understand.
Again, please.
You said P is equal to P0 minus rho Gy. This is only when you have incompressible.
No, it's not the constant density.
But if it is not constant density, it will not be rho Gy.
But I mean, initially, you have two fluids.
But for high density, for high variability density, we have exponential growth.
And no, it's.
Let's say if you take, for example, take ideal gas. I mean, this is integration only when constant density. Pressure is not linear. Pressure is not linear in the incompressible case. It's because rho is not constant.
Okay. I set the simulation.
No, that was steady state. If you take steady state,
Yeah.
highly compressible fluid.
Yeah, but this is the trick here, actually. I set this pressure like this, okay? And then I let them flow, evolve. Okay, so it's not a constant density here. Just initial value, initial density value. It's 1.2 as a low density, and let's say depending on the Atwood number.
Then it will not be Rayleigh-Taylor stability. You get transition flow because you start from a steady state solution. You need to start from steady state and then put perturbation on top of that. Rho Gy is not steady state.
Can you give me some time, because I'm coming some points. Come to that points.
Well, if the density So how do you get the Y part then? Didn't you assume that the density was constant to pull it out of the interval? Isn't that where so you got just the other, so the rho G Y.
Yeah.
So, so that gives you the pressure?
Yeah, it's a distribution, pressure distribution,
Well,
right?
when you integrated the equation, then it's the integral over rho, if rho is variable.
But you're missing, okay, but
So you
I
didn't
see.
do a Taylor series expansion of rho there.
But,
Not
but
that one. No, but that would then be the derivative of rho with respect to y evaluated at that place, right? So that second, is this a Taylor series expansion of the pressure? Is that what you're doing?
again, please.
So you got P is equal to
Yeah.
P naught.
Yeah.
Minus, so did you just do a Taylor series expansion of
Oh,
the
what?
pressure?
Yeah.
And then just kept
That-
the
that-
first
that-
two terms?
Yeah, it was done here.
Okay, I missed it, yeah,
Here, it was done here.
okay.
Okay, it was done here. So I'll take 2 questions if you don't mind. I'm gonna go fast because I'm taking your time. It makes me stress. So here is the examples of Rayleigh-Taylor instability, from astrophysics, from nuclear experiments, industry, and many other natural flows. If you notice, you have to treat body force properly. You have to handle turbulent mixing, diffusion, and interface capturing in the problem. Okay, so many of these examples occur at large density ratios. So there's an interest to solve high Atwood number Rayleigh-Taylor instability, as this is one of my motivations, as I mentioned. Here is the details of the simulation, the length scale, the velocity scale, and this is the time scale of the problem. Okay. This is important quantity omega. At initial, you have to provide a kinetic viscosity to the system. I mean, to the method or algorithm or simulation, whatever. So it depends on Atwood number and your resolution, of course, and it is scaled by this term. So you have to choose this term. You have to choose this term correctly to obtain reasonable and physically reasonable results. It takes some time to determine this scaling factor. Okay, here is the. Actually, I have lots of results, by the way. I computed lots of results, but there's no time. So I'm going to show you just 2 of them. Okay, I'm skipping many others. By the way, I should say that some of the results are computed again for the first time for the high Atwood number multimode Rayleigh-Taylor instability. Okay, including some turbulent statistics. So here is the evolution of the flow when the Atwood number is. By the way, I forgot to mention here, the Atwood number I'm working with starts from 0.5 to 0.9. In some papers, this is called ultra high Atwood number region. I don't know.
Are you doing miscible or immiscible fluids?
Miscible, of course. I mean, okay. Here is the evolution of the local mole fraction, chi or chi in Greek. I don't know. It's a measure of mixing. It takes value between 0 and 1. It shows the development of instability. And as you see here, for the Atwood number 0.5, I set the local mole fraction value to 0.5 again. This time increases from left to right. Okay, for the 0.5, here's the evolution of the local mole fraction. Initially, there is nothing, but in time, the bubbles and spikes are formed, merged, and penetrate into the flow. It starts with a smaller size, and they're getting larger and larger. Okay.
What's your Reynolds number?
Let me see. For this case, here is this value. Okay. Let's compare the different effect of high Atwood numbers. So let's compare the local mole fraction evolution of Atwood numbers here. Sorry, this is the initial. Actually, not initial. The time is 1 in terms of non-dimensional units. There's nothing. Here is the times 3. Difference is, yeah, it's now it's visible. Here is the, okay, this is a non-dimensional time 6, 0.5 Atwood number, 0.6, 7, 8, and 9. Actually, for the 9.9 Atwood number, the non-dimensional time is 5 because the flow has already reached the end of the domain.
What's your stratification vertical?
Again?
Density.
Yeah, aspect ratio, you mean? You're
No, you said your output is 5, yeah?
I'll come to, okay, just wait for a second. I forgot to say some details. By the way, the aspect ratio is 3, and the 2 pi length is resolved by 48 grids, which is, even for an LES, really, really coarse. But there is, if you look at the successful results, let's say, this coarse grid resolution doesn't really affect the performance of the algorithm. So it's a kind of measure for the strength of the algorithm. Grid is very coarse, but results are fine, I think.
But your output number based on interface difference. But what is your stratification?
My output number based on density.
Density difference at the interface. Across the interface. But then you have another parameter, stratification. For example, you can have output number 0.5.
I'm really sorry, my English is broken, so can you tell me using broken English so that I can understand you?
Output number, rho H or L, is
Yeah.
at the top of the domain on the bottom or just across the interface? Because you didn't show the
No.
density profile.
That's valid for the whole domain.
So it's top, bottom.
Yeah. The half of the domain, the upper half of the domain is filled with high density fluid, and the bottom half of the domain is filled with low density fluid at initial.
So you only have difference factor of 2,
Yeah. No, 3. 3. For the 0.5 Atwood number. For the Atwood number 0.9 here, the density ratio is 19. It's quite high.
Yeah, but for output number, if you do stratification, big domain aspect, you can have thousands density ratio.
It will increase the Atwood number.
We can get, let's see your results. I will get to that.
Okay. Here, yeah. We can see that the high Atwood number, Rayleigh-Taylor instability, develops faster than the others. And the forming bubbles and spikes are, you see, larger than the others. So you see this 0.5 is still developing when time is 9 in terms of local mole fraction. So this is the last result I'll show you. If you take the average of the local mole fraction, this will gives you the penetration length for bubble and spike. Okay, and I take the ratio here, HS divided by HB. So if you look at, there are 2 findings here actually. First of all, the 0.5 and 0.6 Atwood numbers have already reached the strongly nonlinear or self-similar region. But 0.7, 6, and 9 haven't reached yet. So this says that for to analyze the high Atwood numbers correctly or properly, you need higher aspect ratio domains. So this is the first finding. The second one, if you look at their values, the ratio increases with an increasing Atwood number. So if you look at the ratio, the increase of the penetration length for spike is much more greater than the increase of the penetration length for the bubble. So this brings you into the flow a strong asymmetry. In other words, spikes develop faster than bubbles as Atwood number increasing.
Was that expected? Was that expected?
Yes, there is only 2 papers in the literature. I confirm their results, by the way. I mean, these results confirm their findings. So in order to provide a scaling between the ratios of penetration lengths and the density ratios, I have to run on a longer domain and of course a longer time. Then I can find their plateau, and then I can give a scaling factor. This is usually given by the papers to you know, emphasize the asymmetry. I'll do that in the full manuscript, by the way. The mixing efficiency, I'm skipping this. The Taylor microscales and the Reynolds number based on, I'm skipping this. Reynolds stress terms, I should say something here. You see the asymmetry of the Reynolds stress terms with an increasing Atwood number. Anisotropic tensors, once you get the Reynolds stress terms, you can easily compute the anisotropic tensor. Another measure for the large scale anisotropy. The most affected component is the B22, is a vertical component. There is no significant change in the others. So I also compute the kinetic and potential energies and compare them. There is no big, I expect that there will be no difference among their values at the end of simulation, 0.4, 0.5, okay. I'm skipping this. I also plotted the subscale dynamic viscosity and outer scale Reynolds number. I'm finishing with this slide. So what I can conclude is the algorithm proposed can handle the high Atwood number, multimode Rayleigh-Taylor instability, physics of high Atwood number, multimode Rayleigh-Taylor instability. This is the first time, to the best of my knowledge, the Rayleigh model is applied to this kind of problem. Results are fine and will be better if I do that on a longer domain. And in terms of Rayleigh-Taylor mixing, I can say that I also computed some of the quantities diagnostics for the first time for that problem. And all are consistent with the previous data. I'm summarizing. There are 2 findings of this work that confirm the other results. The high Atwood number need longer domains and times due to the faster development of flow structures, especially spikes. And this comes with larger asymmetry. Okay, and this brings larger asymmetry into the flow structures. I will provide a scaling factor at the end of my whole simulations, whole work.
Could you clarify, because I haven't seen new presentations, you said you use compressible assumptions, low-Mach number. What is your...
0.1 Mach number is 0.1.
Constitutive relationship between the density and the pressure? Is it ideal gas law?
Yes, but it's not shown here. It's non-dimensional version.
No, it doesn't matter, but it's the ideal gas law.
Yeah, yeah.
So then my point is, what you're doing, you're not solving classical Rayleigh-Taylor stability.
Not
Because Rayleigh-Taylor stability, you start with the steady state solution, and then you perturb interface. By doing linear pressure, it's not steady state at all. You start with the unstable solution.
It's my mistake. Okay, I'll tell you, because I tried to be fast, so I missed some details. Here is the initial perturbation.
No, I'm talking about mean profile. Mean profile is exponential, because if you do this, if you know Navier-Stokes equation, you put a ideal gas law, dP dz equal rho gz, you put, for example, initial condition as a thermal, for example, that T is gone, then you become basically exponential decay in density. Density in pressure are all exponential. So you have very drastic difference, and then you put your interface, if it is miscible fluid, you put interface. So your Atwood number is actually characteristic across interface density change. And your stratification could be thousands. By making it linear, you're putting two problems at once. Number one, you don't start with a steady state solution plus perturbation. You start with a solution which is not steady. So your interface will develop until you develop exponential, number one. So you're mixing two problems together. So I mean, I think you need to work with change initial conditions to make it really
Change what?
initial conditions. Because if you solve the steady state equation, it's not linear. It is exponential. Because you have to solve TBD is equal rho G.
I'm steady state, you mean?
Steady state.
But my equations are not steady state.
Initial condition, when you start with the classical Rayleigh-Taylor, you get steady state solution. Then you perturb interface.
That's actually what I did.
But your steady state is not linear.
How did you decide that?
You set this ideal gas law. Go
But-
to the equation.
But okay, it's not shown here. The ideal gas law is also make it non-dimensional. So
Yes, I mean all these terms are gone. All these terms are gone, and you have this and this term left. So you solve.
yeah. Please enlighten me because if I'm missing something.
Let's assume it is y, yeah? dp dy is equal whatever you do 1 over fruit rho g.
Yeah. Yeah.
So now you assume in initial condition, you're solving for steady state initial.
But you are thinking in terms of Business assumption. I don't apply the Business assumption.
No, I'm doing low-Mach approximation. So then you do.
Okay.
Then you do.
I guess you're Vasiliev. Okay.
So then.
I read your papers many times.
So then you do.
If you give me a minute, I'm gonna thank you. Thank you for having your time. I'm sorry, and thank you again.
Okay, bye-bye. Good luck.